What's up, everybody? First, I had a video about this Foucault Pendulum come up in my shorts recommendations, and then this video by Action Lab where they're driving down the road and fire off a Nerf gun backwards at the same speed that they're driving forward. And I just took this as a sign from the universe that I should do a video about whether or not we're actually moving sitting here on Earth right now, or not. This is something I've actually looked in quite a bit back in the day. Actually spent a couple years trying to prove that the Earth was a pancake. And if you've never tried to prove through independent observation, just completely clear your mind of everything you think you know and go out and make your own observations. It's a lot harder than one would think to prove conclusively what the shape of our terra firma is or whether we're moving or not. It's been a long time since I thought through these things, and I do forget things over time, so this will kind of be like going through the steps brand new again. But let's start off with the Foucault pendulum. A Foucault pendulum is a heavy weight that's usually a metal ball on a long cable attached to a high ceiling. And I think there's even a ball bearing in the top of it. But you can find these in museums around the world. They have a special mechanized release system for this, so that when it's released, it travels directly straight forward and there's no forces pushing it slightly to the left or right. The idea is you want to release it so that it swings directly forward and directly straight back towards you. So you would think that you'd release it and it would swing straight forward and straight backwards until it ran out of momentum, right? The first law of motion is that an object stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. So if you don't apply any lateral force making it go left or right, then it should stay in a straight line. The reason it slows down is because of the force of gravity, or if you don't like gravity, whatever the force is that's making us stick to the ground and not float away. I don't care what you call it, there is some force that makes objects fall down. But what happens is over time, it does start working its way around a circle. This started out going straight back and forth in this direction and has now worked its way around to where it's going straight back and forth in this direction. They say the reason for this is the Earth's rotation, and this is demonstrating it. This was first introduced in 1851 and was the first experiment to give simple, direct evidence of Earth's rotation. The idea is that the pendulum is swinging in a straight line and the Earth is rotating under it, which makes perfect sense. If it's swinging back and forth and the Earth is spinning, then in 24 hours it should have gone to 360 degrees back where it started. But you guys didn't think I was that simplistic, did you? I just wanted to give you time to start typing. This is just wrong on a couple levels. First off, in theory, this would only work at the North Pole, right? If you're over here in North America or Europe, you're at a 20-30 degree angle, and it really doesn't seem to me like it would work at all in this capacity at that angle, but they do have an explanation for it and say that instead of at the North Pole where you have 360 degrees in 24 hours, that you have 270 degrees in 24 hours at Paris. But I don't know, man. Instead of it being a rotational force, now that force would be hitting out and up like this, and I don't think would show anything to do with the Earth's rotation. And the ground wouldn't just be spinning around under it, it would be traveling at that angle along with it around the circle. And then this ties in with my other point. If you were to fly up and hover in a helicopter over the North Pole, would the helicopter stay pointing in one direction while the Earth spins around below it? Well, the official answer is no, because the atmosphere and everything is moving along with the Earth, and you would have had that rotational momentum when you lift it off, so it just stays spinning. Or it's not spinning, and that's why you keep pointing in the same direction. But here's the deal. If you don't expect the helicopter to keep facing in one direction while the Earth spins around below it, then why do you expect the pendulum to do it? The pendulum would be starting out with the same rotational force in the same atmosphere as the helicopter. And like I said, other than at the North Pole, you would expect totally different forces to be acting on the pendulum. I couldn't put this at a 45 degree angle for demonstrations, but that's where the majority of these are set up in North America and Europe. Here at the equator like this, it should just be pushing straight out. And they say that at the equator it doesn't rotate. Okay, but I'll just tell you guys, I've spent about 45 minutes trying to find if there's ever been one set up at the equator. And if this all works like they say, then that should be pretty easy to find. But I can't find any record of one ever being set up at the equator, and I know they have never gone up and set one up at the North Pole. I mean, it would have to be enclosed and out of the wind to have any scientific value. So I'll just tell you, the fact that that didn't pop right up makes me incredibly sus. Okay, so that got me to really digging, and I found a list of all of the pendulum locations in the world. Under Central and South America, you have Chile, Argentina, and way down south in Brazil where the red pin is. And the equator's way up here. All of these are like 30 degrees south latitude. And then the ones in Africa are way down at South Africa and up in Tunisia on the Mediterranean, which is like 30 degrees north latitude. So it would appear that none of these exist within 20 degrees north and south of the equator. Wiki says that they have set one up at the South Pole Station with a beer can and, of course, 33 meters of rope. I don't know. Anything coming out of Antarctica, show me the video, and I'm still probably going to say it's CGI. And y'all got a 100-foot stairwell in there? 33 meters? I'm not seeing it. But if the Earth does not rotate under a helicopter, then how does it rotate underneath this pendulum? That just doesn't add up to me, but that's what they're sticking with. So could there be another explanation for why this happens? What about the pull of the moon? If that's enough to cause the low and high tides, then I'd say that it's possible that this could influence this experiment. But let's move on to the next physics problem here. And if you guys know all this, feel free to skip forward to the Nerf experiment. So if Earth is spinning roughly 1,000 miles an hour at the equator, then the North Pole is relatively stationary. So if you get on a plane and you fly due south, then it seems like the Earth would be traveling 1,000 miles an hour to your left as you land. Right? I mean, if you're going due south with zero momentum to our right from this perspective, then how did you pick up that 1,000 mile an hour lateral momentum? I'm going to leave that open-ended for now and we'll come back to it. And I want to throw in a couple things here. That red line is showing a flight path from West Coast United States over to like Japan or Asia. And I've seen a lot of people use this as an example of why it has to be flat. We think of the world as being like this, so if you're leaving the west coast of the US, it seems like you would fly straight west to get to Japan. And then people get out the azimuthal equidistance and say, look, it's a straight line, so it has to be flat. Well, this actually works whether it's a globe or a pancake, because the northern hemisphere is exactly the same on either model. If you're looking directly down on the North Pole, it's the same on both models. And a straight line is a shorter distance than traveling around one of those circles. We've all seen how flights take an apparently arcing trajectory, when in reality that's a straight line no matter what model you're using. Let's say you're starting and ending at 30 degrees north latitude. If you were to fly around that 30 degree latitude mark, then you'd be traveling much further than the straight line. And since this is measured relative to the North Pole, then that center point is much closer to the pole at like 50 degrees north. So from one perspective, you actually are traveling in a straight line if you're using latitude to measure from. But if you're just looking at a straight on side view, then that straight line appears arced, where your latitude line would appear straight from this perspective. This works the same on both models in the northern hemisphere. Now, I can't believe I found this demonstration that they used on an official science site to tell you why the Earth is spinning, because they actually show the opposite results of this experiment. Let's keep it simple and say at the equator, we're traveling 1,000 miles an hour in this direction, and the red train is at half that distance, so it's traveling 500 miles an hour in this direction. They've got a soccer ball and a goal on the trains, and they ask what happens if you kick the soccer ball at that goal. Y'all got it figured out? Well, the blue train is traveling at twice the speed of the red train, so when you kick the ball, it's traveling at that 1,000 miles an hour to the right, where the blue train is only traveling at 500 miles an hour to the right. So they're saying that the ball has more momentum than the goal, therefore the ball flies out in front of the goal. And what they're showing here actually makes a really good case for why we're not spinning. If that were the case, then if you were to take a flight from Bogota to New York, then you'd have to take off aiming for Texas, because when you take off, you've got an extra 500 miles an hour of momentum, because New York isn't traveling as fast as Bogota. But that's not the way things work. This is an actual flight path. So chalk another one up to we're not moving. Now let's go back to my original example. What happens if you leave the North Pole and fly down to the equator? Is the ground going 1,000 miles to the left underneath you? Now let's look at it in a little different way. What if that were a basketball, a huge basketball? Now what happens if you drive from the North Pole of the ball down to the equator? You would gradually pick up that momentum towards the left. Right here you'd be going 100 miles an hour to the left, right here 200, so on and so forth. So you would gradually pick up that speed. The same principle applies to the globe model because the atmosphere is moving along with the Earth. Otherwise, you'd have 1,000-mile-an-hour winds at the equator. So it would be just like taking flying out of the equation and using driving as the example. But using that same logic for this model, then you would be slowing down with the atmosphere traveling north. But that's not what they show in their model here, which is surprising. So I'm just going to leave it at that, and you guys can make up your own mind. Another problem with all of this is the gyroscope. The momentum of the spinning wheel will maintain its direction in space if the outside framework changes. So if you were to set this up spinning at 90 degrees to the North Pole and then travel down to the equator, well, it would be spinning parallel with the equator. The gimbal that's holding it would have moved over the 90 degrees, but the spinning wheel would still be straight up and down from this perspective. And I'll just tell you, this makes absolutely no sense with a globe model. They use gyroscopes for aircraft, for naval ships, but you can set your gyroscope in San Diego and fly up to Canada and it's still going to be level the whole time. So that doesn't make any sense on a ball. One more quick thing and we'll do the Nerf gun experiment. Mark Robber is one of the Mr. Beast crew, and he did a video that just straight up debunked the Coriolis effect. If you've ever seen this down at the equator, where on one side of the equator it will drain clockwise and the other side it will drain counterclockwise. Well, he did some experiments at his house and then went down and asked the guys that are always doing the experiment for tourist money if he could pour the water in, because there is a big difference on the way that you pour it, and they wouldn't let him touch their setup. He really showed that the whole thing was a scam, and I've looked all over the place for that video and I don't think it's up anymore. And there's a short now that uses clips from that video, but he cut that part out and he says, nope, but the Coriolis effect is very real. So that is kind of weird. He's wildly popular, reaches millions and millions of people, and I think somebody told him to take it down. Okay, now that I've bored everybody to tears, let's see what happens with this experiment. So they measured the speed of the ball firing out of the Nerf gun, and it just happened to be right at about 55 miles an hour. So if he's driving to the left at 55 miles an hour, fires it to the right at 55 miles an hour, then what happens? Theoretically, it should just stay right there in the same spot. And in practice, it sits right there in the same spot. Relative to the camera, the ball is basically stationary as the car keeps driving away to the left. And this actually all makes sense when you think about it. So why is it that if you're at the equator and you fire back opposite the direction of Earth's rotation at 1,000 miles an hour, why doesn't the ball just stay still? Well, theoretically, it actually does if you have a stationary observation point. So if you're traveling 1,000 miles per hour to the right, and then you kick this ball 1,000 miles an hour back to the left, then from our perspective here, if we're not attached to that spinning ball, then the soccer ball will stay in the same spot. But if you are attached to that spinning ball, then when you first kick it, your observation point is right here. But then after, say, 5 seconds, your observation point has moved along with the spinning ball, and now you are over here. So your observation point is moving at that 1,000 miles an hour to the right, while Our position out here not connected to the ball is stationary, therefore the ball has stayed in the same spot. It's the same thing as this. Let's say this is being done at the equator, and this will be easier if we're spinning to the left. So the Earth is spinning 1,000 miles an hour to the left. The car is driving 55 miles an hour to the left, so the total speed is 1,055 miles an hour to the left. The camera is right here attached to the ground, and that is spinning at 1,000 miles an hour to the left. So when you fire backwards 55 miles an hour, that cancels out the momentum of the car. So the speed of the ball went from traveling 1,055 miles an hour to the left to traveling 1,000 miles to the left, the same speed as the camera. Now, if we were standing back here in a theoretical spot detached from all of this, then our observation point would be stationary at the red line, and a second later, the ball and the camera would have moved over to the left by that 1,000 mile an hour gap, and the car would have traveled 1,055 miles an hour more to the left. You see what I'm saying? Our observation point is not stationary. It has the same momentum in it as everything else around. So stationary relative to Earth is still moving 1,000 miles an hour. But from a truly stationary observation point, then your camera and everything has moved. So I'll let you make what you will out of that, and I'm just going to say this. They say that we are traveling around the sun at 67,000 miles an hour, and that the sun is traveling through the Milky Way at 828,000 kilometers an hour. So we're traveling at millions of miles an hour right now. It seems to me like you would have a Doppler effect with sound. It seems like you'd have all kinds of problems if that were true. And I don't know. I find that hard to believe. But I will say this. I've done this a few times out in my inflatable kayak. That's actually the exact one that I've got. But you can be out in the river, lay back and close your eyes, and you can't sense any movement whatsoever. Most of the time, the river's just flowing like 2 or 3 miles an hour, but when you're approaching rapids even, you speed up to 10 miles an hour or so, and you can't tell the difference at all. You also can't tell if you've spun around in orientation either. I'd be facing directly downstream, and I'd close my eyes, and I'd wait a couple, 3 minutes, and try to guess which direction I was facing, and you can't do it. And it's the same thing traveling in a car. You know, if you're on a perfectly straight, smooth road, you can't feel that forward velocity that you're traveling. But even though I do know all of that, it's still really hard for me to believe that we're going millions of miles an hour right now. Anyway, I hope you enjoyed it. Static out.